Hey, hi guys. So let's discuss this problem called shortest path 1. So we are given n cities and m roads, and the capital is located at 1. So there is a node numbered 1, and it's a special node. We call it capital. So the task is essentially to determine the length of shortest path with this capital city, which is numbered as 1, being the source, and the target is to every other city. Right. And the constraints are standard constraints. So the number of nodes is 10 power 5, number of edges is 2 into 10 power 5, and the weights, which is important to note here, are all positive. It starts with 1 and it can go up till 10 power 9. So we might as well store the distance. So the distances might not fit into the standard int data type. Um, so that's one thing to be careful about. Okay. And one this thing that we have already said that okay, the weights are non-negative. Um, right. So the question is essentially the the n cities and m roads can be modeled as a graph, and there is a standard graph problem wherein this boils down to the single source shortest path problem. Here the single source is the capital, numbered 1, and the other cities are the targets. Right. Okay. And so each road is a one-way road. That is also an important fact given in the question. And you can assume it is possible to travel from capital to all other cities. That is, it talks about the reachability. From the city, we can always find a road or a set of roads to any other city. So there is a single component. Um, if we think of it as a directed graph. So this is a directed graph. Each road is a one-way road, and yeah, that's all we have here. Okay. So initially we take n and m, the number of nodes, number of edges, and as like we initialize the visited array, we initialize the distance array. The distance cannot be more than 118. Um, right? Because yeah. So here also I have like we have redefined int as long long. So wherever you see int, it is basically long long. Due to the reason I said while reading the question, and we just call a simple. So we take the input and we call the usual Dijkstra function, and if everything works fine, if the Dijkstra is implemented fine, we can assume that the distance array will essentially be okay. That is the source, which is city one, to any arbitrary ith city for this distance will be stored in this dist or dist array. And so we run the overall Dijkstra. So one being the source, the distance to it is 0. We put we make a priority queue, and we push this this node. So this is essentially node and distance. Distance from where? Distance from the source, which is 1. So that is pushed, and then we run the usual Dijkstra algorithm. We first get the value, and the value, the first element will be the node, second element will be the weight, and we assume that it is processed, so no more pushing its adjacencies to the priority queue. So we just pop it, And yeah, if it is visited, then we just continue. This is trivial, and we mark it as true. That is it is visited, and then we go over all the neighbors of the node, um, and we ask the question that okay, previously reaching to this particular node, this particular neighbor, did I get a better path? So this is up till I reach the node from the source, this of node, and then we add the weight of the edge from node to neighbor, and we ask that okay, if this is strictly smaller than what we have achieved up till this point, so we can relax it. So we modify the distance, we relax it, right? We push it to the priority queue. And when all of them are processed correctly, it will essentially tell us the shortest distance from source 1 to every other node. So that's essentially the solution to this problem. So as we can see, the number of nodes uh, that can go into the priority queue will be at any instance in time. How many nodes can be present? Well, it will be order n, right? And we are going over all the degrees of uh, here, all the degrees of the graph, sum of all the degrees, that is essentially 2e. So for each e, let's call it e, I'm pushing back to the priority queue and I'm hopping from the priority queue, which at any arbitrary point in time will contain n, at most n nodes. This is n. So m log n, m log s is the complexity of the entire